So I'd now like to hand over to Gareth Pender, and in doing so, thank him very much for standing in at short notice to chair the lecture we're about to hear in the question and answer session. Thank you, Gareth.
Thank you very much, William. It really is a great pleasure for me to be here tonight to chair this lecture by Peter, Troubled Waters, Big Waves Beneath the Sea Surface. I'm looking forward to it very much. William's already given you a brief overview to Peter's career, but his day job is Professor of Fluid Dynamics at the University of Dundee, and he's also Director of the National Telford Institute. For those of you who don't know, the National Telford Institute is the Scottish Funding Council's research pooling initiative that covers civil engineering across the whole of Scotland. So in many ways, Peter is an adopted civil engineer, although he did graduate in mathematics and physics from the University of Newcastle upon Tyne, both as an undergraduate and as a PhD graduate. Following this, he spent 2 years as a postdoctoral researcher at the University of Stockholm, broadening his international experience. And since then, he's been based in Scotland, actually having spent 34 years at the University of Dundee, working in the physics of density currents and stratified flows. During this time, he was elected a fellow of this society, and also has been elected a foreign member of the Norwegian Academy of Science and Letters. Truly a remarkable achievement. So I'm sure we're all looking forward to hearing Peter's lecture, and I won't take up any more of the time handing over to Peter.
Thank you very much, Gary, for those kind remarks. And I want to say, first of all, how honoured I am to be awarded this medal. And I want to thank the Society for the award, and particularly to the colleagues who have nominated me for it. It's a particular thrill to be associated in this way with the name of Lord Kelvin. It seems that I've been aware of Kelvin's name since I studied physics and fluid mechanics starting about 50 years ago. I think I'd known of the Kelvin circulation theorem, Kelvin-Helmholtz instability, and Kelvin waves. And I even remember being taught about Kelvin's calculation of the age of the Earth when I was forced to study geology in my first year at university. So thank you very much, and thank you for coming tonight to attend this lecture. Tell you what I plan to cover tonight. I want the topic of my talk is internal waves, and in particular internal solitary waves. These are particular kinds of waves that exist in stratified flows, and in particular exist beneath the surface of the sea in many, many marine environments. So I want to talk a little bit about the circumstances under which they exist. I then want to describe a little bit about their ubiquity in the marine environment. As you see there, I've listed the oceans, seas, fjords, lakes, river plumes. In all of these marine environments, internal waves and internal solitary waves can be detected and measured. I want to talk particularly about, so far as observational work, to talk about internal solitary waves in marginal seas, shallow marginal seas, where they have particularly high amplitudes and where they have particularly strong effects. So I'll briefly mention the consequences of having internal solitary waves in these areas, particularly for the offshore industry, where there is where for many of these locations there is a lot of oil-related business going on. After I've given you that context, I want to talk a little bit about how we've tried to understand the behavior and properties of these waves in a mathematical sense and in a physical sense. And that will involve me in describing to you the various modeling investigations that my group has been concerned with over the years. And I'll try to show you some what I regard as fairly interesting aspects of these waves as we determine them from laboratory experiments. And I should say right at the outset that the modelling work that I've done has been primarily laboratory-based, although I've been very lucky to have had very bright PhD students and postdocs who know much more mathematics than I do and have been able to make contributions in that area. And then finally, I'll try to point to a few areas in this topic where I think new challenges exist and where I think research in this topic might go in the near term. Okay, let's move on to these internal waves then. And the slide that I've got here, I think shows particularly well what I mean. So here, what I'm showing here are two images, or at least two temperature records from a stationary vessel situated here on the continental shelf, just off the state of New Jersey. And this vessel is recording temperature continuously. So up here we have depth, along here we have time, and the colors that you see here represent different temperatures. So you see immediately on both images that we have warmer water on the surface, particularly seen here, colder water in the deeper parts of the water column. For those of you at the back, this goes from the surface down to about 60 meters, and the elapsed time here goes up from 0 to 120 minutes. So you see that the interface between the cold water at the bottom of the water column and the warm water at the top of the water column is characterized by this irregular form here. And in some cases, as in this case here, you can see that the interface between these two regions of the water column is very periodic, and it's indicative of waves being present in that region there. You see waves being present here, but these are obviously not periodic. But they show a generally wavy type appearance, and they are indicative too of waves existing on the interface between the warm and the cold water. And you can see that close to the surface there is almost no perturbation to the isotherms. So these are waves which exist well below the surface, and in particular you can see perhaps that the isotherm here, which starts at this time at a depth of 20 meters, has gone down to 40 meters here. So the isotherm is being pulled down, being displaced downwards by 20 meters in a total depth of probably about, I think, about 800 meters. So those show quite a good illustration of the type of phenomena that I want to talk about today. Well, the first person, I think, to record observations about internal waves was Benjamin Franklin in the 18th century. And he records in a letter to a friend that he had been en route from Madeira to the United States, or to America as it then was, and he had improvised a light which he had hung from a support in his cabin. And this lamp, a so-called Italian lamp, consisted of two layers, a layer of water and a layer of oil. And there was and by means of a cork and a primitive wick, he was able to concoct this lamp. And what he said was that though the surface of the oil was perfectly tranquil and duly preserved its position and distance with regard to the brim of the glass, the water under the oil was in great commotion, rising and falling in irregular waves. So these are some of the early observations of internal waves, waves that existed on the interface between two fluids. And the reason that they can exist is because of the stratification in the water column. So on the left you see a schematic diagram of the density variation with depth. So here we have the surface with a density of about 1.025 grams per cubic centimeter, going down to 1.027, if I can read it there. So we have more dense water in the bottom of the water column, we have less dense water at the top, and in this case we have a linear decrease in density in a region which we call the picnic line. These are actual data that are collected in the Andaman Sea, and on the left you have temperature profiles, in the middle you have salinity profiles, and on the right the resulting density profile resulting from the two contributions of temperature and salinity to the density. So you see here that you have an upper layer. For this location, there's an upper layer, quite shallow, pretty much uniform density. There is then a transitional layer here in which the density increases with depth, and then below about 120 meters here, there is another slight increase in density with depth, but a much more gradual change than we see in this transitional layer here. So it's because of the existence of a density stratification that internal waves can exist. And the reason that they can exist is because if any disturbance acts upon the water column and lifts a heavy particle, let's say from here, vertically upwards, the heavy particle finds itself in a light environment and therefore sinks back again. As it sinks back, it overshoots its original position and finds itself in a heavy environment, so rises again. So the buoyancy in the density profile provides a restoring force that allows waves to exist within interfaces or indeed throughout the water column. So that's the restoring force that we bring in, that we take into account to explain the existence of waves. So if there's a sustained disturbance to the water column, the energy from the disturbance is able to travel away from the forcing region in the form of internal waves or gravity waves. Well, the first person to, I think, explain some of the consequences of internal waves was Nansen in his Fram expedition. And he recorded a lot of details about what is called the dead water phenomenon. Dead water has been known for over 2,000 years, where sailors had realized that when they were either under full sail or at least at full power, the vessel in which they were traveling would suddenly come to rest and would sit dead in the water and was not able to move forward, at least until resting in that position for a while. So Nansen was the first to really get an idea of why this was happening. And he during his voyage with the Fram in Franz Josef's land, he encountered this dead water phenomenon as he came close to regions in which there was melting ice. And he expressed it in this way: we approached the ice to make fast to it, but Fram made hardly any headway in spite of the engine going at full power. The speed reduced to 1.5 knots in the dead water. And then, this is the key point, the water on the surface was almost fresh from the melting ice, whereas through the bottom cock of the engine room, we got perfectly salt water. So he realized that the dead water was associated with the existence of density stratification in the water column. And when he came back, his colleagues Bjerknes and Ekman were able to come up with the explanation. And the explanation is that all of the energy that's coming from the vessel is going into generating internal waves beneath the vessel. And I've got a demonstration of that here. So we're looking in the side here of a tank which is made up of 3 layers. It has a layer dyed green here which is concentrated salt water. We have a layer which is dyed red, which is fresh water, and then a layer of intermediate density between. And we're going to drive this small model boat from right to left. And as it does so, it will disturb the water column. It will displace the interface downwards, and you'll see that it will generate internal waves as it travels. So this boat is driven with a constant force, and the interesting things happen when the boat reaches this region here. So we see the internal waves being generated. These are relatively large amplitude waves. You can see they're comparable with the fluid depth. The boat is going along quite happily. The waves are building in amplitude. And you see now that it's brought to rest. When it's brought to rest, it's no longer generating waves, so they dissipate, and then the motion can start again. And this is a zoom of the same thing. I won't play the whole thing, but you can see the waves in much more detail now. And the camera is going to pan with the boat after a while. The interesting thing here is also you see this fine structure on this interface here, which is indicative of some eddying and some instability of that interface. And I'm going to come back to that later. So here it's reached the point at which the dead water phenomenon comes in, and then it goes on beyond. Okay. So we're talking about internal waves, and I want to now just switch to talk about waves which have very large amplitudes. Even the ones that were in that short movie, you could see had amplitudes that were comparable with the fluid depth. But some of the waves that have been observed, as you can see, are very, very large amplitude waves indeed. If we look at the ones on the left here, these were recorded. This is again a time record of temperature at a station on the Oregon Shelf. And you can see here that the waves are very large amplitude. So this is 5 meters here, and that isotherm between the red and the yellow has been dragged down to 35 meters. So that is 30 meters amplitude, or 30 meters deflection, in a total depth of what is about 5 meters. We see the same thing here. These are measurements taken in the South China Sea, and you can see here that this isotherm has also been dragged down from about 20 meters here down to almost 170 meters here. So these are very, very large excursions, and we certainly couldn't say, therefore, that these were linear waves of the type that we consider in linear theory. So when we have to analyze these waves, we have to bear in mind that they're highly nonlinear, and we have to use the appropriate theoretical background to explain them. Well, these waves are found all over the globe, and these red spots that you see here denote the locations where they've been observed. I want to draw your attention to two things. First of all, you can see that they've been observed in the deep ocean here, as well as in coastal regions and shelf regions. A lot have been observed in the Bay of Biscay here, but in particular, a lot have been observed from the northwest shelf of Australia, South China Sea, the Andaman Sea, and the Sulu Sea here. So relatively shallow compared to the deep ocean, and these seem to be regions in which these waves exist. And this is a slide which summarizes their properties. I should say that sometimes these are referred to as internal solitons rather than internal solitary waves, and there is a fine distinction between the two, but it doesn't concern us here because we're not dealing with the collisions of these waves. We're simply looking at their propagation on interfaces. So this is the important point here, that they are non-linear waves and they're of permanent form. In other words, they travel without changing their shape. And in the ocean, they travel for hundreds, sometimes almost thousands of kilometers without changing their shape. The internal waves that I show here are waves of depression. So you can see that the lines of constant density have been depressed, but there's no peak to the wave. I should say that also waves of elevation are observed in the ocean, but they're much less common. And I'm going to be mostly talking about these waves of depression. So they conserve their form because they maintain a balance between nonlinearity, which will tend to steepen and sharpen the waves, and dispersion, which will tend to broaden them. So by maintaining this balance, they maintain their form. When they're observed in the ocean, they propagate as wave packets, usually with the largest amplitude being the leading wave, and there may be typically 2 or 3 waves in the wave packet. They travel with a velocity of about 8 kilometers per hour, and they are coherent with over large distances with wave fronts typically 100 kilometers, and their wavelength is typically 2 to 5 kilometers. They're observed through radar imaging. Synthetic aperture radar is used to detect them, and you can see how that works, I hope, by this figure on the left. So here's the packet of waves. The waves themselves have associated regions of convergence and divergence, and they produce a textural variation in the sea surface, and the synthetic aperture radar is able to pick up these textural differences, convert them into dark and light, and show up the position of these waves as they travel. So these are images taken in the Sulu Sea. This island here is about 5 kilometers in scale, and you can see a rather beautiful array of these waves here. This is also showing a synthetic aperture radar image. This scale here is 5 kilometers, so you can see that this scale here is also just less than 5 kilometers. So these are large waves which exist in the water column, but they produce an effect on the surface which is relatively small, but which can still be detected by radar. And this is the kind of effect that you see on the surface as one of these packets of internal solitary waves travels underneath a vessel. You can see this change in texture associated with the passage of the wave here, and observers report increased surface roughness, and some of the observers report noise and buffeting of the vessel as the wave goes underneath. The wave here may be 200 or 300 meters below the surface. Well, here are some of the biggest ones ever recorded. I've listed these two here. In the South China Sea, internal solitary waves having an amplitude of 150 meters have been recorded in a water depth of only 340 meters. And in Northwest Australia, amplitudes of 83 meters and 124 meters depth have been recorded. And just in case you have any difficulties in knowing what that kind of scale looks like, St. Peter's is 108 meters to the top. Nelson's Column is 53 meters. So you can see that these are very, very big features indeed. And this is an image here from the South China Sea in a total depth of 900 meters, and this depth is 90 meters. This depth is 180 meters, and here you can see that this interface has been depressed down by about 90 meters as the internal wave goes through. So these are really big phenomena. Before I continue on along this line, let me just divert a little bit to a bit of a controversy. Two American submarines, nuclear attack submarines, were lost in the 60s. The most famous is probably the Thresher, which was lost in 1963 in a depth of about 2,600 meters from a position about 350 kilometers east of Boston. And 129 people were killed. The Board of Inquiry reported that problems arose with the submarine when appeared to arise when there was a leak in a pipework system, and the leak caused the nuclear reactor to shut down. So the submarine was essentially immobilized at its depth. And at the time at which it was immobilized, it was at a depth of about 400 meters, which was within the picnic line, and that was the depth at which the submarine was traveling to avoid detection. 400 meters was about its design depth, but there was a factor of safety of about 25%, so it was held to be safe at that depth, but that its crush depth would be something like 500 meters. And the speculation is that the Thresher, being immobilized at that depth, was caught by one of these internal solitary waves and was caused to descend below its crush depth, and it perished because of that. And when the remains of the submarine were located, it was thought that that the remains showed evidence of implosion having taken place. The Scorpion is a similar story. That was lost in 3,000 meters of water close to the Azores, also a location where internal solitary waves were known to be very common. And I think the explanation there is that the same thing may have happened to that vessel as well. Well, let me get back now to the internal solitary waves which are present in the water column. The essential point about them is that they have very high induced velocities associated with them, and they have very high velocity shear associated with them. On this diagram here, this is the leading internal solitary wave in a packet. And what you see here is a velocity profile shown schematically. And you see that when the wave passes an observer, there is an induced velocity field above the wave, which is in one direction, and an induced velocity field in the lower part, which is in the opposite direction. So there's a strong shear across the wave itself. And these waves can induce velocities of about 1.5 to 2 meters per second in the upper part of the water column and a little less in the lower part. Now these are high velocities. Typical ocean currents are centimeters per second. So these are much, much higher velocities than we would expect just from background currents. It therefore follows that if any structure is placed in the way of these waves, then they will get quite a bang as these waves go past. I should say also that many of these waves are generated, in fact nearly all of them, are generated by tidal flow backwards and forwards over bottom topography, over banks or sills or over the continental slope. So they're generally generated with a tidal period, so they arrive, for example, every 12 hours at a given location. So if an offshore platform, for example, is placed in the way of these, they would expect to be hit by these waves every 12 hours or so. Well, here are some of the incidents that have been reported and which have been ascribed to the effects of the solitary waves hitting the structures. So, reports of tilting platforms, 3 degrees, it's quite a lot. Increase in anchor tension of 25% as one of these waves passes the platform. Off Angola, a rig was tilted by 4 degrees. Another rig was displaced more than 4 meters vertically. Other rigs displaced up to 200 meters horizontally by the impact with these internal solitary waves. And various technical difficulties here that you see, stresses on drill pipes, drill string breakages, drilling downtime, typically 10 days per year in the South China Sea, have been reported. Fatigue damage to moorings and to risers. Quite a costly set of damage. And the estimates are that millions of dollars are required for rig positioning costs and correcting for excessive rig listing. And the list goes on. So in response to that kind of damage record, there was a soliton early warning system set up about 4 years ago to try to see if it was possible to give some advance warning to particularly oil rig installations and particularly in the Andaman Sea. So the generation area for the internal solitary waves is here, and these waves then travel out and cross the Andaman Sea, and there's a lot of oil activity in this area here. So at 2 locations here, a set of instruments were put in place, and these instruments measured the stratification in the water column, they measured the velocities in the water column, and in particular, they could detect whether solitary waves had been generated. Solitary waves are only generated under particular conditions, when the stratification is just right and when the tidal frequency is just right, and in addition, when the topographic details of the bottom boundary are just right. So they don't exist throughout the whole year. In this region, they exist, I think, for about 6 months of the year from May, pretty much all the time. But in the other periods, they are detected occasionally. So the idea would be that these instrumented arrays here could detect the waves, and that the information that they were coming could then be telemetered to the rig, and that the rig could then take some kind of preventative action. So this is the setup. Here's the rig. Here are the two sets of instrument. Here they're measuring velocities, temperatures, and so on. And here are the internal solitary waves. And with this arrangement, preliminary warning could be given about 16 hours ahead of time. These things are moving at about 2.5 meters per second. And 11 hours before their arrival here, a full specification of the solitary waves could be given. In other words, the speed and the direction could be given, and corrective action could be taken. Well, you can see that this is a rather dramatic picture. You can see that the helipad on the rig has been tilted significantly away from the horizontal, and that's even after the warnings have been received and after appropriate action has been taken, particularly through tensioning the moorings. One particular difficulty that oil rig operations have to be aware of are the positioning of floating production, storage, and offloading units, FPSOs. These have to be positioned very, very carefully when they're offloading from an oil rig, and they have to be aware of when the waves are coming, because when the waves come, they can easily move these vessels off station, and they can be very difficult to control. So here is an example of where a procedure can be instigated to guard against the solitary waves. You see the solitary waves are coming in from this direction here. There is a band of them here. And this shows, if you like, the worst position for the FPSOs to be in. So what they do is to just move themselves around using some kind of weather vane procedure, so that when the waves actually appear, they can be the line of the vessels can be perpendicular to the crests of the internal solitary waves as they approach. And indeed, I was speaking to somebody from BP, actually trying to get money out of him to do some work on this, and he said that this is regarded as the biggest problem so far as oil rig operators are concerned. How to maintain the FPSOs on station with a high degree of precision when internal solitary waves are traveling. Well, I now want to talk a little bit about some of the modeling work that I've been doing. And I mentioned before that I've been fortunate to have very, very good colleagues to work with me on this. And I wanted, just before I show some of the modeling results, to pay tribute to the efforts of Yakun Go and Magda Carr, who are both postdocs with me. They now have positions at Aberdeen and St Andrews. And also to Jon Grue, my colleague in Oslo, with whom I've worked for about 10 years, looking at some of the characteristics of these internal solitary waves. So I want to talk a little bit about some of these modeling investigations. I should say that internal solitary waves have been studied for many, many years, and there's a good understanding, a good theoretical understanding, a good mathematical description of their behavior. The aspects that we wanted to look at in our experiments and our modeling studies was the effect of the shallowness of the water. You will see from those examples that I've given you earlier that the amplitudes of the waves are nearly always comparable with the depth of the water column. And that means that the bottom boundary, the sea floor if you like, must play an important role in determining the properties of these waves. And I can remember Clive Greated, who's sitting in the front. He and I had a meeting with somebody from Amoco many, many years ago who told us that the big uncertainties in this field are what happens very close to the sea floor when we have shallow water columns and big internal waves. So that's really been the first emphasis, and I want to show you a little bit about what we've done there. So we're interested in the importance of the bottom boundary. We're interested in knowing what happens close to the boundary. And this just shows the laboratory setup, and indeed the theoretical model setup that we've used to look at waves of depression. So imagine here that we have a tank, a long tank here, which we fill with 3 layers of fluid. We're going to use salt water to give us the density difference rather than to use temperature differences. For practical reasons, salt and fresh water are much easier to work with in a laboratory. So here we have a layer of salt water of density rho 3 and depth h3. On the top, we have a layer of fresh water of density rho 1 and a depth h1. And in between, we have a transitional layer in which the density increases with depth linearly. So this is linearly stratified, this is homogeneous, but rho 1 is less than rho 3. We have a gate at the end of the tank, and we have the same setup behind the gate as we have in the main part of the tank, except we have an excess of fresh water here. We have an excess volume V of fresh water here compared to the amount of to the depth of fresh water that's in the main tank. So what we're going to do is to remove that gate, and when we remove that gate, the flow will adjust itself and we will generate an internal solitary wave which will travel from left to right, and it will depress the lines of constant density in the method shown. So the internal solitary wave will then move from the left to right with a characteristic speed c. I'm going to talk first of all about waves of depression, and we get waves of depression when we have a thin layer above a thick layer. We can get waves of elevation if we have a thick layer above a thin layer. So we can set this up to look at both types of waves. But I'm going to talk mostly about internal waves of depression. So I'm going to show a short movie here, but before we do that, let me just explain what we're looking at here. This is a false color image, so the colors have no meaning whatsoever. This is the bottom of the tank here. This is the top of the tank here. And throughout these two layers, we've sprinkled tracer particles. We put the tracer particles there because we're going to visualize the motion of those tracer particles as the wave travels from left to right. By looking at the tracer particles and by measuring their displacement in a known time, we can come up with the velocity field throughout the bottom layer and throughout the top layer. Now, these neutrally buoyant particles are not fully neutrally buoyant, and they tend to collect at the interface. So you can regard this as being the upper layer, this at the lower layer, and this the transitional layer here. So I'm going to raise a gate at that end, and you'll see a wave of depression come towards you. I hope. So you can see the disturbance to the surface because as the gate has been opened. This is much slowed down from what it would be in practice. So you can now see that the wave of depression is approaching. And as it approaches you as a fixed observer, you see that the flow in the upper layer is to the right. The flow in the lower layer, which is just beginning to accelerate, is to the left. So you can see the strong shear across any vertical line there. So everything is behaving quite well. I think the trough has almost come to the center of the frame. So the back part of the wave is now starting to appear. And I'll just move this on a little bit. So now the wave is almost passed. The velocity is reducing here. But I just want you to put your attention to the bottom parts here. And you can see that now that the wave is gone, you can see evidence of a thin boundary jet that's formed here, which is flowing in the opposite sense from the main flow that was there while the wave passed. And I think our group was the first to detect this boundary current and the first to measure it. It had been predicted theoretically, but had not been seen before. And this is just a graphical illustration of it. Here we have a time series here. So here we have the horizontal velocity in the way associated with the wave. And we measure velocity profiles at different heights above the bottom. So this is the approach in the forward part of the wave, and you can see that all of the profiles sit on top of each other. But in the aft part of the wave, so the wave is approaching, here's its maximum, and then this is the aft part of the wave, you can see that these different profiles diverge. And in particular, the blue and the red profiles have a final value for the velocity which is non-zero. And that's because these are associated with the generation of that jet that I showed you, the boundary jet. Just a quick an explanation. We think that this is due to separation. For those of you who fluid dynamicists in the audience, we think that the bottom boundary jet is a result of boundary layer separation in the adverse pressure gradient at the back side of the wave. If we look at the pressure on the bottom, the pressure is high here, low here, and high here, both due to hydrostatic pressure and due to the dynamic pressure associated with the wave. So here the pressure gradient from positive to negative is in the same direction as the pressure gradient driving the flow, whereas here in the aft part of the wave, the pressure gradient is in the opposite sense from the pressure gradient driving the flow. So we'd expect to see separation in this region, and that indeed is what we see. We've done some comparisons with the Bergen Ocean model, which is a numerical model. These are the lab experiments I've just described, and I don't want to go through the details of this very much, simply to say that this is the predicted profile from the numerical model. The model was set up to exactly replicate the size and density differences in the experiment, and you can see this general agreement between the shapes here. So if we translate this to full size, we can say that this boundary jet that we've talked about has a depth of about 20 to 30 meters, and it has a maximum velocity of about 10 centimeters per second. And this is quite a high velocity to have very close to the sea floor. Well, if we force that boundary jet even more vigorously than we did last time, using exactly the same situation, exactly the same configurations before, we see that it becomes unstable. So what I'm going to show you now is another movie. What you see here are velocity vectors, and they're scaled to show the velocities in the bottom layer here. So because of that, when the main wave goes past, you'll just see a mess of black. But as the wave passes, this is highly speeded up. So the wave is coming, it's gone, the peak has gone past now. And now you see the jet being formed here, and you see that after a certain time it becomes unstable, and it produces these large circulating eddies. And this, we've looked at the instability of this jet and have got, again, quite good agreement with theory. You can see that as a result of this jet instability, you can see that the disturbed region here is much higher than the thickness of the jet. So we have evidence here of the boundary jet, when it becomes unstable, producing effects at some distance above the level at which the instability is generated. And the consequences of that are quite nice. This is a sequence that was lent to me by a colleague in Queen's University in Canada. And what we have here is the bottom of the tank here. This is the interface between the upper layer and the lower layer. So it's a slightly different setup from that I've shown you. But these particles here will show up the wave as it passes. And you'll see that, you'll see that what happens when the wave passes is that the boundary jet becomes unstable, and small particles that are on the seabed are lifted up and suspended into the water column. Here's an example which doesn't have false color this time, but we're now looking at what happens when one of these solitary waves impacts upon bottom topography with a corrugated form. So we have the same setup as before, except we now have a corrugated bottom. So we would expect the flow in this layer to be from right to left, flow in this layer to be from left to right. And this flow from right to left you'd expect to separate at the peaks of these corrugations, and you see it happening now. You can see these tip eddies being formed by this main flow here. But remember, when this wave has gone past, we'll generate a current in the opposite direction. And we'll see as this proceeds that this bottom current which is generated has the capability to lift off these eddies and propel them vertically. So we now have the wave pretty much past, and we now have the reverse boundary current forming, and you can see that this small eddy has been lifted off, and its effect has propagated almost to the interface. And in fact, you can see a deformation of the interface there. So bottom topography has a really strong effect on what happens very close to the sea floor when one of these large internal waves passes. Well, if we move our attention now not to away from the seafloor, and we ask what happens when one of these internal waves reaches a very, very large amplitude, can they break just like surface waves break? And this is a sequence which will illustrate what I mean, and I'll just advance it slightly. So the wave is approaching. This is a really high amplitude wave. This is no longer the bottom of the tank. So we have the flow going from right to left, flow from left to right here. Strong shear across the interface, and you'll see that that shear causes the interface to become unstable, and you see the appearance of these typical billows from here to here to here. So these are relatively intense. As you can see, there's a strong overturning motion here. These exist as isolated billows, or in some cases we get pairing of billows here. And you can see there's a lot of disturbance downstream as well. So these waves, these billows, when they are produced as a result of the shear instability of that layer, can have big effects in mixing dense water here into light water here and vice versa. And this shows how those billows develop. These are just frames taken from the record. So the initial perturbation is here, very close to the trough of the wave, and this perturbation then just rolls up, as you can see, into a billow like this. You can see that the vertical scale of the billow is increasing as we go from this time to this time. It's grown to there. You can see a strong wrapping around of the particles that were in the interface. And then you can see this blurred effect here, and this blurred effect is due to refractive index variations, which show up the mixing that's taking place within the billow. So already you can see that the water from here has been mixed into this layer and vice versa, and there is strong mixing across that interface. And this shows it in particular. So what has happened has been that this billow has grown until a certain critical height. The buoyancy associated with the stratification of the water column prevents it growing any further, so it collapses. And as it collapses, it generates turbulence. And you can see that this is just a mess, that the nice clean lines that we saw here in the early growth of the instability is lost here. So this mixing process is very important. It's very important in the oceans too. This wave breaking that we've seen here is almost certainly a manifestation of Kelvin-Helmholtz instability, which is the classical shear instability that we see in natural flows, but also in idealized flows. So this is an example of Kelvin-Helmholtz instability generated by the numerical model. We have a layer of dense fluid here, a layer of light fluid here. We have and there is a difference in velocity between the two layers. So the effect of the shear under certain circumstances is to cause that interface to become unstable through Kelvin-Helmholtz instability and to cause these characteristic billows that we see here. And these are examples where these billows have been observed in the atmosphere, where there is wind shear and there is temperature stratification in the atmosphere. So there are many, many really pretty examples of Kelvin-Helmholtz instabilities in the atmosphere. Here's an example of an optical backscatter image taken on the Oregon Shelf, and you can see the kind of thing that we've just seen in the laboratory experiments, perhaps not as well ordered as we saw in the laboratory experiments, but you can see nevertheless evidence of this overturning and billow formation. So this is the internal wave of internal solitary wave, the lower interface. This is the upper. The wave is going in this direction. So you can see that the instabilities, when they occur, are generated aft of the trough. And that's what we see in the experiments as well. So the conditions of shear that are suitable for the generation of these billows occur downstream of the trough. So we've been trying to look a little bit more about how much mixing these billows cause, and I'll show you another sequence here. So we're looking in the side of a tank which is stratified, and we've got a gate at the left side. We're going to open the gate, and we generate an internal solitary wave that we know will break. And when it breaks and produces billows, we have a series of spears here, microconductivity probes here, that we're going to drive vertically through. So these spears go right through the center of the billows, and they record what the detailed density structure is within the billows. So you'll see this is a speeded up image too. And I'll show you a couple of times. So here we go. This is a composite from several video cameras. Now you see the wave starting to appear as the wave goes towards it, and the probes go through to try to capture what is happening inside the billows. I'll show that again. No, I won't. So the billows are forming, they're growing, and as you can see, they're pairing. As you go further away from the crest, you see all of this turbulence that's generated by the billow production and by the billow development and by the pairing of individual billows as the flow develops. Well, this is a typical signal from one of those probes. So this is a probe which measures the salinity. It has a very fast response. So by driving the probe very fast through the salt stratified system, it can pick up the very, very small turbulent fluctuations in salinity. And it's this probe here that we're looking at, and that has gone through the center of that billow, and this is the signal that it shows. So it picks up the homogeneous layer in the upper part, and then as it goes through the center of the billow, you can see the deformation of the density profile. So this was originally linear before the wave came. And the effect of the billow, as you can see, is to produce this circulation, which has brought heavy fluid here into this region, and which has taken light fluid here down into this region. And you can see that it produces this rather typical density signal which indicates circulation. So I won't go into details about this, we've been doing a lot of work in taking these kinds of signals and comparing them with the undisturbed signals and trying to estimate how much turbulent mixing is taking place within these individual billows. It turns out that all the mixing takes place within the billows, and between the billows, here and here, there's almost no mixing whatsoever. Well, if I have time, no, I think I'll move on. So we've done many, many modeling experiments, and we've done accompanying theoretical work as well, numerical work. These are the problems that I think are going to be important in the future. This problem of sediment resuspension by the passage of internal solitary waves, I think, is very important, particularly when there's a lot of seafloor infrastructure which can be damaged and the surrounding sediment can be eroded. There's quite a lot of work which indicates that internal solitary waves, when they pass through particular regions, can cause problems for these remotely operated underwater vehicles, and indeed the military have looked at this, and it seems that the solitary waves can affect the methods of mine detection as well. I think there's a lot of work to be done in the numerical modeling of the breaking process that I've just shown from the laboratory experiments. I think there's a lot of work to be done on mode 2 waves as well. I'll say a little bit about that in a second. Because this is a kind of springy system, which the water column, when it's stratified, can admit many different modes of internal waves. It has to, the equations of motion have to satisfy boundary conditions on the sea floor and on the sea surface, and within those boundary conditions, a bit like a stretched string, you can get a fundamental mode and harmonics. Well, in the same way here, one can get mode 1 waves, which are the type I've just shown you, and mode 2 waves as well, and I'll show you some examples of that. And I think there'll be a very important, there's a very important area of research opening up here when these internal solitary waves interact with the continental shelf, particularly since there's a lot of oil rig investigations close to the continental shelf. And then perhaps even as the oil business moves north, there may be some interesting scientific problems thrown up by looking at the effects of ice shelf conditions and how they affect the propagation of internal waves. So here's just to illustrate what I meant. There's lots of seafloor infrastructure, as you can see, cables, pipes, manifolds, storage facilities, and so on. And particular problems are encountered, I think, when internal solitary waves approach a continental shelf, as I'll show you in a second. The waves break on the continental shelf and produce lots of turbulence and can, in principle, produce lots of damage as well. This is a deep water environmental laboratory that's just been installed in 1,400 meters of depth, and that's due to be there for 25 years, I think. And this will have a number of instruments, and it will sit in a region where, in principle, there's a big risk of erosion of sedimentary material by the passage of internal waves. We've made some progress with mathematical modeling. This paper that I've cited here with our Norwegian friends was quite successful. We were able to look at modeling these really highly nonlinear waves, large amplitude waves, and getting quite good agreement. So for cases when the waves were not breaking, the colors that you see here are from the laboratory experiments. It's a time series of the elevation of the interface. And you can see that the mathematical prediction holds quite well with the experiments. The opposite is true when the wave breaks. So this is a time series, so this is the approach of the wave, this is the backside of the wave when we have breaking occurred. And you can see that although the mathematical model models quite well the approach of the wave and the part of the wave just upstream of the trough, it of course can't treat, at the moment, can't treat very well what's happening when the waves break. Well, here are some recent numerical experiments done by the group in St Andrews, trying to look at breaking waves. This is in the frame of reference of the wave, so you're traveling along with the wave all the time, and you can see that the numerical model replicates quite well the generation of these billows and the pairing of the billows here. So at least in qualitative terms, the numerical model can give quite a good representation of what we see in the laboratory. Now quickly I'll talk a little bit about mode 2 waves, and these are waves where there is not just a wave of depression, but there is a wave of elevation as well. So these are sometimes called convex waves. So these are internal solitary waves as well. They travel much slower than the mode 1 waves that I've been talking about already. And you see them in oceanographic measurements. There's one here. It's associated with a train of mode 1 waves. But this is a typical mode 2 wave, and it has an amplitude of something about 15 meters, so not as big, not as energetic. Well, we've been looking a little bit about these, and I thought it'd be fun just to show you this. So this is a mode 2 wave we generate in the laboratory, and you can see when it comes that it's quite different from the mode 1 waves I've been looking at so far. So this is a particular case where there's lots of mixing going on here. lots of mixing going on there. Evidence of shear instability and billows here. And the mode 2 wave is gone, and it's got this tail attached to it, which is wavy because it probably has a tail of mode 1 waves. But you see the main characteristic of this is that the fluid inside the tail is being dragged along with it. So these mode 2 waves, as well as carrying energy, they can transport mass and particles and nutrients and so on. This is an attempt to show that mode 2 wave that I've just shown before and superimpose upon it the velocity vectors that we measure. So you'll see the velocity field and, whoops. You see the velocity field, which are the small arrows, and you'll see the mode 2 wave as it transmits from left to right. Don't worry about the colors. For any fluid dynamicists in the audience, these are vorticity contours. Well, I see that my time is almost up, so I thought I'd just talk a little bit about this last problem that I thought is important. There's a lot of oil activity now in the Faroe-Shetland Channel, northwest of the Shetlands. This is a very deep channel, and it's a region in which internal solitary waves are found rather often. And there was some interesting work done by Hosgood and Van Haren to instrument the side of this continental slope here, to look to see what happened when the internal solitary waves came up against the continental shelf. So this is the continental shelf here, this shelf here, and we have various instruments at different depths. And it was found that at this depth here, 471 meters below the surface, the temperature record showed very, very sudden and almost instantaneous drops in temperature, here and here. And these drops in temperature were associated with the arrival of internal solitary waves and the breaking of internal solitary waves on the shelf and the propagation of tongues of cold water up past the instrument. And you can see that here. So here you have the slope. Here you have the cold water, the blue, and you can see that the blue water has been driven up the slope here. And the result of driving that cold water up the slope here is to produce lots of turbulence, and these small intense regions here with red attached to them are areas of very high energy dissipation, very high turbulence, and suspended sediment measurements here show very high peaks, very close to where this internal solitary wave has broken and this run-up of cold water has occurred. So I think that that's an area where there's a lot of work to be done by modelers and even by oceanographers. So in conclusion then, I hope that I've made this topic attractive to you. I hope you've seen where there's the intellectual challenge in trying to understand these phenomena and where there's a practical relevance to understanding these internal waves. The subject of internal waves is a very old one, it's a very mature one, but there's been a big growth in activity and research in this area in the last 10 years, and I think in the next 10 to 15 years there are many, many opportunities for young people entering the field of environmental fluid mechanics to really make some big impressions. So I'll leave that with you. Thank you.
Thank you very much for that, Peter. We've got some time for some questions. So are there any questions from the audience? At the front, if you could just wait till the microphone arrives.
More an anecdote than a question, but I've got a second point to make at the after that. 40-odd years ago, I was a submariner in the Royal Navy, and in a patrol submarine weighing 2,500-odd tons, 100 yards long. This is the days when thermionic valves were transitioning into white spot transistors and red spot transistors. So in order to do a low-frequency sonar search, with the hydrophones mounted along the length of the hull, we had to circle at about probably 360 degrees every 30 minutes in order to do a full scan of the ocean. And we were off Ireland in the North Atlantic on the continental shelf. And when we were roughly pointing north-south, parallel to the continental shelf, we were rolling 45 degrees either side with a time interval of probably about 2 minutes between one cycle. Was that due to the effect of a storm throwing waves onto the continental shelf, or was that due to ISWs?
Well, ISWs are generated primarily by tidal flow over topography, but they can be generated by storms as well. If the storms persist for long enough, they distort the density interfaces, and if the storms are growing long enough, the interface can reach a stable level, and then when the storm is stopped, then the interface relaxes, and in some circumstances, the relaxation of the interface, the upper layer and the lower layer, can set off a train of internal solitary waves. You actually see this process quite often in lakes, in very large lakes, where a wind is blowing over the lake, sets up a longitudinal gradient in the interface, and then when it relaxes, there's a seiching produced and the generation of internal solitary waves. So it could have been that as well. I think in the region where you describe this anecdote, internal solitary waves are observed. They're not, I think in that region, not particularly large amplitude, not compared with some of the big, really big waves that we see in South China Sea and the Andaman Sea. I mean, was the vessel displaced upwards and downwards as well?
Not that I can remember, no. But it's a long time ago.
Yeah.
But it was certainly, rolling 40, 45 degrees either side, and that in a submarine is really quite startling.
Yeah. But this last set of observations that I just described, where you see what happens when a solitary wave does indeed come close to the continental shelf, you can see the generation of this upslope current, sometimes called a solly bore, a bit like the bores that you see in rivers, like the Severn bore, for example, which is a gravity current which is driving up the slope at really quite a high velocity. So if you were close to that, I guess.
Well, at 400 feet, we're in the right ballpark for your chart,
yes.
Your graph.
Yes.
Yeah. The other point I'd like to make was, as a submariner, 40 years ago, we understood that Thresher sank because submarines in those days had a large volume of internal pipe work, which was at seawater pressure. A small gauge connection failed, and the spurt of water, the jet, at 400 meters would have been considerable, but containable. But that jet of water hit the electrical switchboards and cut off the power to the pumps that provide heat from the nuclear reactor to the steam generators. The steam generators drive the turbines and also the AC generators. And so if you have a flood in a nuclear submarine, the only thing to do is to go full ahead and fly the submarine to the surface, whereby the seawater pressure declines. And hopefully you can get enough air into the tanks to stay on the surface after you're half full of water. So that is my understanding of what happened to Thresher, and similarly to Scorpion.
Yes, I think the Board of Inquiry report certainly doesn't say that it was due to the presence of a solitary wave, but there has been a lot of discussion about that. It's still an open question, I think.
Unhappy days if you're a submariner.
Yeah.
Thank you. Excellent.
Any further questions for Peter? Yes, Clive. Could you just hang on till we get the microphone, Clive? Yeah.
How important what are solitary waves for marine life? I mean, you talked a lot about oil exploration. What is really the significance of internal waves?
Well, they're very important in generating vertical mixing, in transporting material, nutrients, I guess larvae and so on, large horizontal distances and large vertical distances. Internal solitary waves are different from linear dispersive waves, which carry energy but no mass. The internal solitary waves can travel very large distances and can take sediments, nutrients, larvae with them. So in that sense, they're important for the distribution horizontally and the distribution vertically of those species. But so far as bigger orders and fish and so on, I have not seen any reference to effects of that type.
To that, though, is global warming?
I mean, internal solitary waves exist only in the circumstances when the stratification of the water column is just right, and when the topographic features are just right, and when the tidal frequencies are just right. So if there are changes to the temperature of the oceans, and those changes are felt more in one part of the water column than the other, then you would expect that the shape of the density profiles within the water would change, and they would affect the occurrence or otherwise of the internal waves. So I think it's, in general terms, any warming of the oceans you would expect to see an effect.
Okay, thank you.
Question in the middle.
So sort of following on from that, so the sharpness of the interface seems to be critical, and the layering, the thickness of that top layer seems to be critical. Now, global warming is causing the polar ice caps to melt, and so you're getting lots of fresh water pouring onto the dense salt water. Also, when you see the ice caps melting, if you've been at the snout of a glacier, you get big chunks of ice falling off. Are they capable of creating these internal waves at the interface? And is there any evidence for increased frequency of internal waves at in the northern hemisphere, close to the?
Not that I know of, Bill, but the scenario that you describe is a bit similar to the situation on the west coast of Scotland. There is the tidal force at Loch Etive forces fresh water out on a tidal cycle, and when that water is expelled on the ebb tide, is it? When it's expelled, it can generate internal solitary waves ahead of it. So whenever you have, whenever you have an increase in surface flow of fresh water, you have the possibility to generate internal solitary waves. It depends, I think, upon, as you said, depends upon exactly how much fresh water is being supplied and what the ambient density stratification is before the discharge starts. It's an interesting point.
One more question in the back at the middle.
Mike Ford, University of Edinburgh. Thanks for a great presentation. I've got two questions. First one is, did you win the money from BP? And the second one is, has the offshore industry taken on board all these new developments, and are they being incorporated across the exploration world?
Yes, I think they have. Last year, I organised, together with support from the Royal Society of Edinburgh and the Norwegian Academy, we had a workshop in internal solitary waves, and it was the third in a series, but this time we attracted 2 or 3 people from industry as well. So I think there is certainly an interest now in industry in the research that's going on in internal solitary waves. And I think that interest will grow. I think there's a particular interest in this sediment erosion and sediment resuspension, because it messes up subsurface communications, acoustic communications. It has the potential to erode cables, pipes, manifolds, and seafloor installations. I think that's where the main interest is at the moment.
Okay, question at the front in the middle, and then we'll go to the gentleman behind. Sorry, could you just so people at the back can hear, could you hold on to it? Yeah. Come to you next, yeah?
I want to pose an entirely different model. I'm a pathologist, and we're concerned with diseases of the aorta, which is a vessel about over an inch in diameter, which takes most of the output from the heart to the rest of the body. Now, there is a very common condition called aortic aneurysm, and we know exactly what causes this in most cases. There is a degenerative state in the wall, which weakens it, and the wall expands and sometimes ruptures. I just wondered if some of these ISWs might play a part in causing aneurysms, expansions, bulges in the aorta, independently of degeneration in the wall. In other words, it's being hammered from the inside. If this sort of wave can be generated under those conditions.
My wife was looking at me because she knows I'm extremely squeamish. And so I'm glad the question has stopped there. I think in general, solitons, solitons, or solitary waves, occur in many, many different fields. In fact, I think optical cable transmission is often by means of solitons. So the question is whether the mechanism that is driving the blood through the vessels that you describe has the characteristics to generate solitary wave type disturbances that can travel through. I don't know the answer to that. I can see in the audience someone who has worked a lot on the fluid mechanics of blood flow, and he might be able to answer this question. But it's an interesting question because you have a flexible boundary there as well, and it can, in principle, I suppose, support solitary waves traveling through it. It's normally the blood is normally propelled by peristaltic effect, I suppose. Yes, yeah. I'd have to know a bit more, but it's an interesting. Yes, it is. Yeah. Yeah. Yes. Yeah. Mm-hmm.
So can we take one last question in the centre at the front?
Thank you, Peter, for a very interesting talk. My question is on whether research has been done about the interaction between a buoyant plume from the seabed going up and internal solitary waves. So say there was a deep well blowout in the Faroe Shetland Channel, what would the effect of a buoyant plume going through the interface interacting with waves be?
Well, if it was a plume of oil or oil material, I would think that the interaction of the oil plume with the propagating waves would be probably one of deflection rather than entrainment. I don't know of any work that's been done on that area, but that's what I would expect to see. The passage of the internal wave takes quite a while compared with the typical timescale of the buoyant plume. I would think that there would be some effects of deflecting the plume if it's a vertical plume, and if it occurred next to a continental shelf or very close to the slope, there could be some entrainment as the wave breaks. But if we're talking about the interaction and of the plume and the wave a little bit away, I would have thought it would just be a deflection. I don't know of anything that's been done on that so far.
Thank you.
Now I'd like to call upon my colleague, Professor Vladimir Nakora from the University of Aberdeen, to offer a vote of thanks.
Thank you, Gary, and Good evening to everyone. It is real pleasure and honor and privilege to express on behalf of everyone here our deep appreciation of this fascinating and truly insightful lecture with many stimulating ideas, excellent, appealing examples, and captivating animations, particularly exciting animations revealing very interesting physical phenomena. It's not first time when I have opportunity to listen to Peter's lectures, but every time I'm fascinated with Peter's research, and today I found his lecture particularly interesting and stimulating. I could talk a lot about Peter's work that he presented today, but I would like to highlight only one issue among many discussed this evening that relates to hydrodynamic instabilities, the role of hydrodynamic instabilities in generating and in the dynamics of internal waves. Because this issue links directly Peter's lecture to Lord Kelvin's work. At the beginning of his lecture, Peter mentioned that Lord Kelvin not only pioneered many engineering areas, mathematical models, mathematical theories of heat, electricity, and other subjects, other areas, but he also laid foundations of fluid mechanics. It's less known fact compared to, for example, contribution of Lord Kelvin to electricity theory or magnetism. And among many important contributions of Lord Kelvin to this field of fluid mechanics, one of them is relates to shear instability, well-known today, widely well-known today as Kelvin-Helmholtz instability, which has very direct relevance to the physics of waves that Peter discussed today. That from this perspective, we can consider Peter's lecture as a very important tribute to Lord Kelvin's work. I also would like to highlight the tradition of fluid mechanics research in Scotland. I would call it groundbreaking research or cutting-edge research, which not everybody likes, and I fully agree. But it's indeed fluid mechanics research in Scotland has a very significant history, very significant impact on world research in fluid mechanics, and we have special feature of this research that combines theoretical analysis, complicated, sophisticated analytical methods with physical intuition, with very sophisticated and innovative physical experiments. And I would like to particularly stress the importance of Peter's work that over many years he was serving as a guard of these significant traditions in fluid mechanics research, which is very important for maintaining this line, this tendency, this trend in our work. And I don't want to take much of your time. Everybody probably tired, although the lecture was very interesting, but that time is a little late. Therefore, I would like to join me in congratulating Peter for a really superb, inspiring lecture this evening. Just two more words. I would like to take this